Resume recording here. Hello, everybody. Ah, I need my ears. I need my ears. So today we did cadmium selenide nanoparticles in the lab, right? And, you know, one of the things about this story that kind of tickles me a little bit is that it's just all shake and bake, you know, chemistry, you know, just add stuff together and particles just form, you know? Like if you like there's a whole bunch of different metals. If you add a reducing agent, the particles will just form in the solution. And it's not really that big a deal. I mean, that there's obviously there are going to be conditions that favor producing small separated particles, right? But you know, I don't know. That's I shouldn't dismiss any of it because you know, much smarter people than I am are working on it, you know, and they're working through all the ins and outs and how exactly to make the particles, you know, from the proper starting materials and how to control their sizes. And then in some cases you can control their geometry. And like an easy way to think about that is you put them in there with a surfactant that works mostly on one crystal face as opposed to the other, right? Because when you make the nanoparticles, they're crystals, right? The atoms come together and they usually form, you know, hexagonally close packed crystal structure or something like that. You know, if they're binary, cadmium selenide, maybe the size difference and the stoichiometry can dictate a different chemical structure. But in order to make different shapes, you just find a way to passivate certain parts of the structure for additional growth, right? So it's pretty easy to make gold nanorods by adding acetyl trimethylammonium bromide, and that's called CTAB, and CTAB is a soap, and that trimethylammonium group has a big long greasy tail. That's the acetyl part. I think it's C16. So it's a saturated 16 carbon hydrocarbon, and then that will naturally form micelles. You know, it will go into solution and it will form um, uh, these spherical structures with the fat on the inside and the polar group on the outside. You know, and so if the CTAB, if the trimethylammonium or possibly the trimethylammonium bromide, it could have bromine in there. If they associate closely with, say, the 100 or the 101 or whatever crystal face of gold is, but not with the 111 face, right? Then what'll happen is that the crystals, as they're growing, they'll grow much faster in the 111 direction, and then you wind up with rods or wires or whatever you want to call them. So in any case, I think it's kind of amusing and interesting and fun that there is much more variety in the way that you can form that. You know, I'm sorry, I'm I'm just lost here. So I'm gonna keep moving on here. So I'll share my foils with you here. So let's see here. Share screen. There we go. So first of all, I didn't check in with anybody. How's everybody doing today? People doing okay?
Pretty good.
We're a little bit. Yeah, that's good. That's good. Let's see.
I had a delicious salmon with like salmon leftovers from dinner last night with some pesto veggies.
Oh my God. Oh my God. That sounds wonderful.
Yes, it was very good.
I literally just choked down a 7-Eleven chicken sandwich.
I can't eat chicken,
and here's
so
my.
I'm sure that was good.
Is that a moral choice or is that a biochemical choice?
Moral.
Oh, is okay. So are you pescatarian?
Yeah.
Basically?
Yeah.
Okay, cool. He only eats fish. Of the living critters, he only eats fish, right?
Yeah.
Fish and maybe like seafood.
Oh yeah.
How about bugs? Would you eat?
Oh yeah, I've eaten bugs.
Would you eat bug?
I've eaten bugs.
Okay. Okay. Who else has eaten bugs? Nobody else here has eaten bugs or will admit to it. At one time I was very young and I was fed crickets and I think I ate them. I'm not really sure, but it was at our creepy neighbor's house. I mean, they've been our friends for life, right? But at the time they were pretty creepy for me. But
I think that like cooked,
yes.
I've had like cooked crickets before. Obviously not like live, but
Oh yeah. I've never never eaten them raw. I was like,
yeah, they're pretty good.
that's good. Oh God. Oh my gosh. So are there any other vegetarians or vegans or Ankita, are you vegetarian?
Well, like earlier in my life, I used to be like full on vegetarian, but then I eat chicken and sometimes fish now. But yeah, I mean, sometimes I decide
Is your family
that I want to be vegetarian, or
Mm.
sometimes I feel like having chicken. So, kind of, I guess.
Could I ask a sort of a forward question? My dearest friend is my dear friend, Dr. Sharma. He's Brahmin, right?
Yeah.
And do you come from a Brahmin
Yes,
background?
I do.
Yeah. Dr. Sharma, according to him, has never touched caffeine or alcohol
Yeah.
or any animal product in his whole life.
Yeah, my parents like they're fine with it because
Oh, that's good. That's
they
good.
don't
Yeah.
really they're not very religious or anything
Good.
about that. But
Good. I mean. Well, I shouldn't. Like. I'm just glad that they're not sort of pressuring you. That's all.
no, they allow me to eat whatever I want, so it's
Yeah.
kind of nice.
Yeah. There are days that go by when the only thing I eat is caffeine, alcohol, and things with faces. That's by the way, one of the other rules for dietary rules is don't eat things with a face, right? That would rule out pescatarians. But then you could eat like shellfish. But then if you're Abraham from an Abrahamic religion other than Christian, you can't eat shellfish, right? You're Muslim or Jewish, right? You can't, and there's probably some Christians who can't either. Depends on which books they follow, But I don't know about this. I was vegetarian in college for a good number of years, and I'm trending back now because my son is vegan, which is, oh my God, vegan is so hard because you can't eat anything with milk because I don't know, it's like, and they're all ethical considerations. So like, what do I tell my son? Like he's teaching me ethics. It's like, okay, I'll go along with you. I'll be a good boy. Anyhow, so thank you for checking in. Thank you for sharing your dietary idiosyncrasies with me. Is there anybody else that wants to share about their day? Per favor. All righty. Well, let's jump on in then. So, the question of band structure in carbon nanotubes is an interesting one because it's a two-dimensional material, right? So you can compute the bands, and normally what they do is they compute the band for electrons that are moving along the axis of the tube, right? And that seems pretty straightforward, right? And you can totally do that. You can totally do that calculation in most cases, right? You saw in the STM image that there are these interesting twists that you can get in a nanotube, and so they show up in the density of electronic states, which is what actually is being probed by the STM tip, although it's not hard to infer the atomic positions from that. And you can see that for that there are at least two types of tubes in terms of their band structure. There's conducting tubes, or metallic tubes, I should say, and then there's semiconducting tubes, right? And so in this picture, right, of a metallic nanotube, this is the density of states along the tube axis, right? And it's an interesting case of a material with both an inner valence electron transfer optical absorption, and also which are also metals, right? Most metals they have they don't have this optical transition. Copper is an exception, right? Copper and gold, they both have that yellowish color, and so they both have an optical transition and are conductors. But in this case, you know, this metallic band that they calculated this for has an interband transition, and it's also a metal. So if I were to ask you to tell me what electrons at what state contribute the most to the conduction of this tube, what would your answer be?
Valence electrons?
Well, you know, it's interesting because there is no real distinction between valence and conduction here, right? Because if you were to, you know, pack more electrons in, it would destabilize the structure of the tube. But that doesn't quite answer my question, right? My question is, at what energy level? Would it be along here, along this large density of state plateau V1? Or would it be up here? Or would it be up here? Where do the electrons contribute the most to the conduction? So this is now sort of a multiple choice. You have three possible answers.
At the energy level 1?
Okay. Wehan, what do you say? What do you say?
I think it would be at C1.
At C1, okay. Danielle?
I'm not sure.
Okay. That's a good answer. Who wants to ask me a question about my question?
Wait, okay, can you repeat the question, please?
Yes, I can. So now we're into multiple choice territory. What electrons contribute the most to the electronic conductivity of a nanotube with this density of state diagram?
And
Electrons right at the V. Go
oh,
ahead.
how do we,
Electrons right at,
I was just gonna say, how do we determine what you mean by contribute the most to?
good question. So there are electrons at this energy level and this energy level, and maybe at this energy level, right? The green versus red means what here? These green horizontal lines versus these red horizontal lines. What does that indicate?
Conduction versus valence?
Yeah, that's a very good deduction. It's not quite right though. You know, it's actually it's probably true, but
Is it bonding versus anti-bonding?
yeah, that's also true. But how about populated versus unpopulated? So if you were to have a microscope that could answer the question, are there electrons at this energy level in this carbon nanotube? Would you get the answer yes or no?
No.
All right. What do you think, Caleb?
I'm gonna say yes.
All right, Caleb's gonna say yes. Who's gonna, so now we have two teams, Team Caleb and Team Vigo. Let's pick teams. Team Caleb says there are electrons at this energy level. Team Vigo says there are not. Wehan, to whom do you ally, Vigo or Caleb?
I'm gonna have to go with Caleb on this one.
All right, Brian?
Caleb.
All right. Oh my. Raymond?
I was also gonna go with Caleb.
All right, Sadana?
Yeah, I was gonna go with Caleb too.
Sahoda?
Yeah, I'm Team Caleb.
Okay, already. Ion?
I was the team with there's no electrons there. I forgot.
Okay, Team
Team Vigo.
Vigo? Vivian?
I'll go with Vigo. No.
Team Vigo? Thank you. Fiona?
I guess Caleb.
Team Caleb? Lucas?
I'm gonna say Caleb.
All right, Team Caleb. Jimin?
Caleb.
Caleb? Emma?
Caleb.
Celine?
I don't know. Caleb.
All right, Rohan?
I'll go Vigo.
All right, Rohan goes with Vigo. Chris?
I'm gonna say yes. There are electrons in the conduction.
Okay, that's Team Caleb. Danielle?
Caleb.
Team Caleb. Caleb is Team Caleb. Vigo is Team Vigo. Ankita?
I'm not sure because
Team no team.
I don't see.
All right, Jerry. Jerry?
He typed it in chat. He said he went with Caleb.
Okay. Jerry is Team Caleb. Astra?
I'm not sure, but I would say no electrons.
Okay. Team Vigo. Tavleen?
Team Caleb.
Team Caleb. Max Wang?
Caleb.
Caleb. Alicia?
I'll say Vigo.
Team Vigo. Essence?
I'm going with Caleb.
Team Caleb. And Rachel?
Vigo.
Team Vigo. All right. So the answer is Team Vigo, because there is most definitely no electrons in the conduction band. That is too high of an energy. The electrons fill up to a certain point, and that point for 10 extra points is called, that level is called the what level?
Me?
Yes, whoever you are. Ha ha. Whoop whoop. Okay, what team? Or what
Is it,
what level is that called?
is
Where
it
the
called
electrons. Mhm.
is it called the ionization energy? Or
It's very related to ionization energy. Ionization energy is the amount of energy it takes to take an electron from there out to infinity.
Is it
Yes,
the Fermi level?
it is the Fermi level. Team Caleb gets the Fermi level. But Team Caleb does not get the maximum credit for understanding what the Fermi level is, because that's the highest occupied level at 0 Kelvin. All right. So, so now, given what I've said about this, what electrons contribute to conduction? Obviously, you can't have conduction band electrons contributing to conduction in this metallic tube. Any of these vacant states don't contribute, right? So which ones contribute? And what do those electrons have to do with the aforementioned level? Okay, so let us consult our friend Wikipedia. Come on, come on. Okay, blah, blah, blah. This is what the Fermi level looks like as a function of temperature, right? At 0 Kelvin, it's flat, right, at some level. But as temperature goes up, it stretches out, right? And if we look at, and this is the functional form, this is called the Fermi-Dirac distribution, right? It's super important in science, in basically all solid state science, right? This distribution. This tells you the state occupancy relative to the Fermi level given uniform density of states, right? So what does it mean that the temperature is high and we get more high level and fewer low level electrons? Okay, what does it mean that as temperature increases, as T gets larger, this term goes to 1/2, right? At T equals infinity, you've got e to the 0, which is 1/2. Otherwise, you've got this function where at T equals 0, you've got 1. Right? And this is for E equals mu, right? Equals the Fermi level right here, which is 0.55, right? So what does it mean that as T increases, we get more higher energy electrons and fewer lower energy electrons? Who can answer that question?
It would mean that the electrons are being excited.
Exactly. What electrons are being excited to what states?
They're being excited to the Fermi state and the valence electrons.
Are they being excited like past the Fermi state to the conduction band from the valence
Yes. Yes. To the,
conduction?
right, from valence to conduction. There we go. Sorting this out, right? Now, why is the population always equal to 0.5 at this level, 0.55 EVs here? Because 0.5 is, or 0.55 is the Fermi level, right? So at 0 Kelvin, the electrons will be perfectly populated below this level and perfectly empty above this level. But as temperature increases, then electrons from here are excited into here. Does that make sense?
So electrons are excited from the valence zone to the conduction zone.
Yes, they are. Yes,
Okay,
they
and
are.
what exactly is the conduction zone, just so we're clear?
So in this case, they're just names that we're giving to electronic states that are above the Fermi level and below the Fermi level, respectively. Now, based on what we said earlier, electronic states above the Fermi level are most likely, though not absolutely certainly, they're most likely anti-bonding levels, right? So what happens if that's true, if the states above the Fermi level are anti-bonding and below they're bonding, then what happens at T equals infinity?
Everything
Then
would
we
be in the
get,
conduction.
well, actually exactly half would be in the conduction and half would be in the valence band, right?
So that line would become like just a linear line.
Right. It would be a horizontal, it would be a sort of a diagonal line, right? Anyway, I'm not exactly certain about that, but I am certain about the supposition that there are an equal number of electrons in the valence and conduction band, equal number of electrons above the Fermi level as below, as temperature becomes very large, right? So, Sadhana, question for you. What happens when electrons go from the conduction band to the valence band in terms of the structure of the nanotube?
I have no idea. Like,
Okay. Who else? Does anybody else have an idea what happens to the structure of the nanotube when electrons go from the valence to the conduction band, or from the bonding to the anti-bonding level?
Random guess, they collapse.
What collapses?
The nanotubic structure.
There you go. Yeah, that's we could say that the molecule dissociates into atoms, right? There's no longer any net binding energy to hold the atoms together, and they come apart because they're hot and they can do that, so they do it, right? Does that make sense? Brian, can you paraphrase what I just said?
Can you say it again?
Sure. When the bonding and anti-bonding levels have equal population, then there's no net bonding and the molecule dissociates.
Okay.
Cheers. Okay. So who else? Celine, can you paraphrase what I just said?
You were talking about band theory. Sorry, I'm kind of confused right now.
Okay, that's all right. That's all right. That's all right. I'm actually talking now. We could relate what I'm talking about now. Oh, geez, what is that? Oh, that's something on my screen. Oh, geez. Anyway, so what I'm talking about is how electrons can be in bonding and anti-bonding orbitals, right? So when electrons come together, the states available to when atoms come together, the states available to electrons partition into bonding and anti-bonding states. The bonding states, they will contribute to a net binding energy for the nuclei to be at a certain radius, right? They'll hold the atoms at a certain distance. Anti-bonding electrons will tend to push the atoms away. So like it's almost like if two people met on the battlefield, each holding a shield, and the shield was in, then they couldn't bond together and they would go away, right? But if the shield was out, then they could go shake hands, right? Or they could kill each other. But let's say they're going to shake hands, right? So as this nanotube heats up, the Fermi-Dirac distribution predicts that there will be more electrons in the anti-bonding conduction band states than in the bonding valence band states. Well, not more than, but they will partition from one to the other. Does that make sense? Okay. Can you paraphrase what I just said in a certain way, including the weird stuff about meeting on a battlefield?
Basically, when like electrons bond, they can either be far apart or close together.
Uh-huh. Yes.
Yeah.
Okay, so it's not electrons that are bonding, it's actually atoms that are bonding,
Atoms,
right?
okay.
So the atom is at the most basic is a proton and an electron, right? It's this existing pair of protons and electrons. And when they come together, they can bond, or they can just bounce off each other. They can actually feel a repulsive interaction, right?
Does it depend on the charge? Like if they repel or attract?
Yes,
Okay.
it absolutely does. The charge determines everything.
Mhm.
Charge determines everything, right? So last time we spoke, or a while back, I screwed something up a little bit, and I can take this time now to clarify and apologize. But I said that there's I think I said there were 5 Coulombic interactions, but that wasn't quite right. There's when you have 2 hydrogen atoms coming together, right? There's the nucleus repulsion, right? Then there's the electron 1 repulsion. Oh wait, yeah. So there's electron repulsion. Then there's electron nucleus attraction and electron nucleus attraction. Yes, Astra. What was your question?
I had a question a while back. I was just wondering how the antibonds and bonds kind of relate to nanotubes.
Yeah. So that's a good question, and so let me. That's where I'm going with this. So let me go. So so the electrons in this atom, right? This H2 molecule, rather, they can either be in between the nuclei, in which case the most favorable state is at this certain radius around I don't know, 3 angstroms or something like that, or maybe a couple of angstroms, right? And then if that molecule absorbs light, then one of those electrons will be promoted to a higher level antibonding state, right? And that will remove bond strength, right? That will make the bond weaker. As a matter of fact, if you count up the bonding and the antibonding electrons, you can say that they contribute approximately equally to the stabilization or the destabilization of the molecule, right? So whether the atoms stay together or the atoms fly apart depends on this orbital occupation, right? So so that's for hydrogen molecule H2, right? Now, what we see here is this is the occupancy of a uniform density of states diagram, sort of in a metal, right? For low temperature and high temperature, right? So as the temperature goes up, there are more antibonding electrons and fewer bonding electrons. When the temperature goes down, there's more bonding and fewer antibonding electrons. Okay. So how's everybody doing? I mean, am I boring the crap out of everybody right now? Or are we okay?
It's a bit hard to grasp,
Thank you, Lucas.
but
Thank you.
I think I am hanging in there.
Okay. Okay. Cool. So let me ask Lucas a question now. What happens to the net bonding in this molecule as the temperature increases?
The net bonding goes down because you have like an equal amount almost at high temperatures of electrons in
Yes.
higher energy levels and lower energy levels, antibonding and bonding. And then
Exactly
gets
right.
to like zero net energy, then the molecule will dissociate because it doesn't have enough bonding energy to stay together.
Perfect. Perfect, Lucas. You get 1,000 extra points today. 1,000 brownie points. I'm super proud of you. So next time, when it's Team Lucas versus Team Ankita, I'm just kidding. I don't know. I don't know where I'm going with this. Just shut up, Roger. Just shut up. Okay. So now let's look at these state diagrams, right? There's a metal here. And why is this one a metal when this is a semiconductor? This guy's a metal here on the far left, and this guy is a semiconductor, sort of third from the right. So what this is energy, and on the x-axis is density of states. It's the number of states that electrons can occupy, period, in a given direction, right? You could say this is in the axial direction of the nanotube. Jimmy, do you have a thought? Should I take that as a no? Yes, Vigo.
Okay, so you can tell it's a metal because there's an overlap in whatchamacallit, the two pieces. Meanwhile, with the semiconductor, there is no overlap and there's a band gap.
Right. Yeah. So why is there a blob here and then a gap and a blob here? What's that? Lucas.
Oh, I was just going to ask, why is there semicircles? Why are they semicircles?
Oh, it's an arbitrary shape that these people chose to describe the bands. It's not from any theory. Vigo, did you have a question also or no? Are you gone? No, there you are.
Oh, well, just my answer was just the part where it was there's an overlap with the metal and there's a band gap with the semiconductors.
Right. Sorry. So, okay, cool. So how can there be a gap here and then more black states down here? Okay. It's sort of a trick question, right? Because they're there because they can be there, right? Because this hypothetical state diagram says that there's a semicircle, and a semicircle, and it places EF, the Fermi level, right in the middle of this semicircle, right? So why is this state empty and this state filled? Sadhana, can you answer that?
Could you like repeat the information before?
Sure.
Like, I don't think I
Absolutely.
understood that one.
Okay, why is this state empty and this state filled?
Well, I'm not sure. I guess it's like relating to the Fermi level and it being higher, so then or lower, so then that way it hasn't like moved to be in the conduction gap yet or something, or doesn't have enough anti-bonding energy to be like in the white part.
Okay. Who can improve on Sedana's answer? Alicia, can you elaborate on that a little bit, maybe?
I'm not sure how to improve off of that.
Okay. Rohan, can you improve on that?
No, I can't. I'm just sitting here confused.
Okay. All righty. So if you're confused and you have a question that you feel like you can articulate, raise your hand. Okay. So who do I ignore most? Fiona. I've been ignoring you. I've got to pick on you a little bit. Okay. So if you were in a playground and there was a set of sort of monkey bars, right? And there were monkey bars that were right at your eye level, and there were monkey bars that were below and above your eye level, right? And it was a very, very low energy day. And you don't feel like climbing any damn monkey bars. Then I would place you at the eye level, right? So you're not climbing, you're just going to that eye level, right? Now, the next day, you're much happier. You're just thrilled. I mean, it is a good darn day, right? And you climb up the monkey bars and you say, hey, everybody, I'm up here, right? Yeah, exactly, right? But then you're like, oh, I'm a little bit high, and you climb back down, right? Okay, so what does that have to do with these lower states being populated and these upper states being unpopulated?
I guess it's more common to have a bad day than a good day.
I love it. I love it. Yeah. Everybody's having a bad day. Ah. It seems like the rule here rather than the exception, right? So the thing that has to do is that, you know, when electrons and protons are interacting, there's an attractive interaction between the electrons and the protons, right? And if there's a state at lower energy, the electrons will tend to give off energy as photons and occupy the lower energy states, right? Then as more electrons come along, they can't occupy the very same state. Whose principle is that?
Polynomial exclusion.
Pauli. Exactly, Pauli exclusion principle, which leads to the Aufbau principle. You guys remember the Aufbau principle?
The electrons take the lowest energy states.
Yes. Yes. You build up from low energy, right? Which is the entire answer to this question about why these states are populated and these states are unpopulated. Ion, thank you. You get the prize for today. You and Lucas. So now, so this is a metal. This is an intrinsic semiconductor, right? What's the difference between the intrinsic semiconductor and the insulator?
Bigger band gap.
Bigger band gap, exactly. That's all, really. You know, it's like a piece of diamond is an intrinsic semiconductor, but they're not that common because there's a big band gap. Takes a lot of energy. It's like 5 eV or something to get an electron from the conduction band to the valence band. I'm sorry, the valence band to the conduction band, sorry, of diamond, right? Okay, cool. So let's go back here. So people have been thinking about this type of thing in nanotubes a lot, you know, like what determines the electrical conductivity and the thermal conductivity and other things like that. And somebody managed to get a zigzag tube to be stuck between two gold protuberances over an etched out pit in a in a silicon dioxide substrate. Right? So this is gold, silicon dioxide around here. This is vacuum, right? And they could actually see this nanotube using the tip of what's called an atomic force microscope. So the atomic force microscope is exactly what is described here, even though the scale is completely wrong. There's an ultra sharp disparity. It could be a single atom at the tip of the AFM. And the AFM is actually brought into contact with the surface. And in this case, it can be shown that as you stress this nanotube, the band gap increases by 100 millivolts for every 1% of elongation in this nanotube. That's interesting, huh? So that type of thing can be done with an AFM tip. And let's skip this nonsense. We don't know enough about AFM to really analyze this. But this was done on zigzag tubes. And for the life of me, I cannot remember what a zigzag tube versus a zigzag versus armchair tubes are. But I'd like you to think about this diagram for a moment. And think about this vector right here, this purple vector. And this chicken wire in the background, at each intersection point, there's a carbon atom. And each piece of wire in the chicken wire is a carbon-carbon bond. Right, I'm sure you've seen these from Xiaowei already. And in this case, we have chicken wire, which can be rolled such that CH goes around the circumference of the tube, and the axis of the tube extends along these directions here, right? Now, what I would like to offer is that for different vectors n and m, you can also do this rolling trick. And we don't actually have, I used to print this out on paper, right, for y'all, but I didn't quite get to it this time. And it was sort of fun. There was lots of tape and scissors and stuff, but in the end, people had these little tubes of paper and nobody knew what the hell was going on anyway. So it was kind of a wash. Like, I made a tube, but what? You know. But the point of that was the point of that was to teach me how these role vectors work, right? And there's one way to sort of describe this, and that is um, if you look at these at right angles, right? This is a hexagonal CNT lattice, right? Then if you go along the direction where to go from atom to atom, you go left, right, and left, and right, and left, and right, then that is called a zigzag tube, right? Whereas if you go along the direction where it's straight down, straight up, straight down, straight up, straight down, straight up, that's called the armchair direction, right? And most armchairs are type tubes are metallic. Most zigzag tubes are conducting, right? And you know, and then there's actual rules here. The Hamada vector that we looked at earlier is N0, right? And these predominantly semiconductors are semiconducting if n over 3 is not integral, right? So n has to do with the circumference of the tube. And then most armchair tubes are metallic. And then chiral tubes will have their own state diagram. They'll have their own unique density of electronic states. And this, by the way, is one of the reasons that it's so difficult to use carbon nanotubes in electronics, because they all have their own state diagram. And it's very hard to make all the same structure of tubes, right? They can have they can all have the same diameter, but be anywhere from semiconducting to metallic to anywhere in between, right? They can have semiconducting qualities and metallic qualities and all in between, right? So if we go back to this picture here, you could have bye Jerry. You could have this could be a zigzag tube, for example, or I'm sorry, a chiral tube, right? And it could have very poor conductivity because right at the Fermi level here, you have very few states, right? And the electrons along this large state density around here, they're all occupied. Therefore, these electrons cannot contribute to the conduction. Does that make sense? Okay. Ankita, I'm looking at you through my you have a sort of spring in the way, so I have to look at you through the spring in my camera holder. Why, if these states are all occupied down here at V1, do they not contribute to conduction in that tube?
So is it the valence ones that are fully occupied?
Mm-hmm. Yep.
Okay. So I'm not entirely sure.
Okay. All righty. Vigo, do you have a question about this?
Well, my question was more so about the zigzag and armchair orientation because I remember with Dr. Chen, we talked about this, but I remember he said that the zigzag was always metallic and the armchair was semiconducting or metallic depending on chirality. So I don't know which one is really like right.
Yeah. Join the club. Who knows? It could be. It could be. Could be. These calculations are not perfect, right? These are density functional theory calculations, and they're actually really detailed. And they have to go through and solve these things called Green's functions to get the states. So who knows? Yes, Ankita.
I think I might have an answer. I'm not sure.
Yes. Okay.
So they don't contribute to any conduction because that's their existing state or something. I don't know.
Right.
So
Yeah.
I think
It sounds like you're getting closer.
would you
Yeah.
have to apply some energy to them in order for them to be able to conduct? I'm not sure.
Okay. Very close. Very close. Very close. Jimin, do you have any insights on this question or?
Not really.
Okay. Danielle?
No, not really.
Okie dokie. All righty. So, who knows the answer? Anybody? Lucas?
I have a
Do you know?
guess.
Yes, Raymond. Yes.
Is it just because like the gap between like the valence and conduction is too large, so like you can't get enough energy to like put them into the conduction or like the conduction band?
Interesting. Yeah. So, let me tell you the answer to the question. Right. The answer to the question is that any completely filled state does not conduct because of the Pauli exclusion principle. Right? If you can't exchange particles, then you can't have conduction. Right? So now at the Fermi level, or near enough the Fermi level that you have some partial occupation, then you have conduction. Right? And then why don't these states up here conduct? Because they're empty. Right? All righty. Okay. I think you guys are done for today. I think we're done. What do you think? Do you want to talk more? I will go all. Sorry, Viga?
If there's more to talk about, I guess I don't speak for everyone though. I would be fine with
Yeah, I know.
ending.
I know it's completely unfair, isn't it? Well, let's see. So what did you guys do today in lab? Or what was done in lab, I guess?
We just made cadmium selenidide or whatever it's called, selenium anion version of it. We made nanoparticles of that.
Cadmium selenide. Did they show you where those guys are on the periodic table?
No, but I think cadmium is alkaline earth metal, and I think that selenium is a halogen.
Okay. So cadmium is a group, whatever here, 3, right? It's equivalent to group 3, right? Because it's 1, 2, and then 3.
Okay, I was
No,
wrong.
no, it's, I'm sorry, it's equivalent. It's equivalent to group 2, right?
Yeah.
And then selenium, I always base this on carbon, right? It's 2 to the left of carbon and 2 to the right of carbon, right? Carbon's group 4, right?
Mm-hmm.
And then there's 3, 5, gallium arsenide, that's a common semiconductor. And then cadmium selenide, that's a 2, 6, right? So you can have 4, 3, 5, and 2, 6 semiconductors, right? Now, the reason that we don't often use or that these guys, these alkaline earths aren't involved in semiconductors, that they don't have d electrons. At least that's my hand wavy understanding of it, right? So zinc and cadmium and mercury can all form semiconductors with tellurium, selenium, and sulfur, and even oxygen. Zinc oxide is a wide band gap semiconductor, right? I don't think cadmium or mercury bond with oxygen, but zinc sulfide, zinc selenide, cadmium sulfide, cadmium selenide, cadmium telluride, mercury telluride. These are all 2,6 semiconductors. So they all make good semiconductors. And if you need to make a PN junction in a semiconductor, then you give it more cadmium than you have selenium. You sort of overdope it with cadmium. That's one way to do that. Right? Cool. And what color were the nanoparticles?
It depended based on how large the particles were, but I know like the lowest one was like blue or something. Then the more you went down, the darker and like orangey-ish it got.
Excellent, excellent. And why does the color depend on the size?
I think it has something to do with the Bohr radius.
Yeah, 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 exactly. So if you confine an electron, you can think of the conduction and the valence band electrons in these semiconductors as being confined physically within the dimensions of the nanoparticle itself, right? The electrons can't go outside of that nanoparticle without having a great energy barrier, right? So at room temperature, they don't have enough energy to get out of the nanoparticle, right? So the electrons are in states in the nanoparticle that bind them in there, right? Now, when light is absorbed, what happens to the electrons?
They get excited.
Mm-hmm. Mm-hmm. From what state to what state? Or what type of state to what type of state?
Ground state to whatever the other one is called.
Mm-hmm. Ground to excited, yeah. Or also you could say valence to conduction band, right? Now, if the physical size of the nanoparticle becomes smaller, then what happens to the band gap, the difference in the electronic states available to those electrons?
It becomes larger.
Yes, it does. Yes, it does. And that blue shift can be observed in nanoparticles. Right? As nanoparticles get smaller, the band gap separates, right? Very good. Now, let's see. And do these nanoparticles luminesce? Yes, they do. They do, don't they? So if you shine blue light in or ultraviolet light, then you get band gap emission out, right? So you can take electrons from the valence band anywhere in the valence band, and with ultraviolet light, you can promote them into the conduction band into almost any state. Then those electrons will relax down to the bottom of the conduction band. Then they'll wait for a period of time characterized by the half-life of that state, and then they'll fall and they'll emit photons within a narrow range of energy corresponding to the band gap. Right? Do you know why they wait? I mean, there's a sort of a stupid answer. I'll give you the stupid answer, right? Stupid answer is because there's a lower probability of changes for this larger band gap. I mean, it's not just because the gap is large, but relative to the transfers of electronic energy to the thermal bath going down in the conduction band from one little level to another. Those transfers can happen very quickly, and they don't give off light. They just warm up the nanoparticle, right? Then when the electrons get to the bottom of the conduction band, right, then those states are longer lived. And that state will exist for a couple of nanoseconds before it quenches, or before it emits, rather, or it quenches. You know, quenching is also possible. It's if they go down without emitting light, but if they go down and they emit light, then we can sort of time it. You know, you can get an idea of the lifetime of that state by looking at how the state luminescence decays after the light is turned off, after the excitation light is turned off. Alrighty, guys. I think we're cooked. I think we're cooked for today. Shall we break? Oh, yes, Lucas. Yeah, what's your question?
So the electrons just stay in the lower conduction band because they have a higher probability of being there, essentially. So there's.
Oh, absolutely, absolutely. It's, you know, that's basically just because they're at a lower potential energy there, right? They're closer to positive charge, and they're further from negative charge when they're in a more favorable bonding state. That's all there is, you know. That's really the only. That's the critical part of the potential energy term, is the proximity of a charge on average to its oppositely charged partner, right? So, you know, in a band, it's a little bit abstractly kind of weird to define, right? But it's like the wave function of the electron as you go through the crystal has places the electron at high likelihoods of being between the nuclei than in some opposite state where it's sort of, you know, exposing the nuclei to one another, right? It's anti-bonding. That that will correspond to a higher electronic energy level. And I know there's something in that I'm not quite getting right, but um, in a hydrogen atom, it's probably easier to envision, right? That when the electron can squeeze between the nuclei, then it's at a lower potential energy than if it's excited to a state where it's on the opposite side of the nuclei, right? And that's not only higher energy for the electron, but it's also higher energy for the nuclei. And that entire energy penalty is paid by a photon that excites the electron from in between the nuclei to opposite sides of on the same chemical bond. Isn't that interesting? So it's the same penalty is paid, for the nuclear repulsion. But it's basically the difference, between those two states, right? Where there's an electron in between to an electron outside, right? And you do work on the electron, but you really do work on the entire system, right? And so as these electrons move out there, then the amount of work you have to do on the electrons includes the potential energy change for the nuclei as their screening charges get lower. Anyway, shut up, Roger. You don't know what you're talking about. Out of my wheelhouse. All righty. I think I think you guys have done really good today. And I just don't want to beat the dead horse today too long. So why don't we sign off and pick up again tomorrow? Thanks, everybody.
Thank you very much, Dr. Terrill, for the
Bye.
time.
Thank you.
Have a good
Thank
day.
you. Thank you guys so much. It is absolutely my pleasure. Thank you.